Here we go. This is the second part of Module 4. We're going to talk only about pH in this module, but it's a pretty important subject. So here's our pH meter at the soil testing lab. We've got our soil solution. Ooh, went the wrong way. Let's grab a pen here. We've got our soil solution here in the beaker, our pH probe going down in there. This is our base solutions of pH 4, pH 7, pH 10. By putting those into the meter, we draw a line graph of the electric conductivity, how much electricity goes across here, and then we can read that across a line to give us the pH. So these standards are important. They recheck, recalibrate the pH meters about every 1,000 or so samples. And they have, as you can see, a lot of samples. Ultimately, what you get from that on your soil testing report is the pH. Here's a pH of 6.5 for the first sample, 6.5 for the second sample. Those are probably okay. Oop, look, there's one getting a little bit lower. They did not recommend any lime, but this would be a case where you could read more into it and say, okay, we're probably going to need to maybe add a little bit of lime. This is in North Carolina. There's acidifying factors going on. It's a low buffered soil, which we're going to talk about buffering a little bit. We might want to prepare to put lime down next year, or maybe put a little bit lime down this year, so we know it's going to move slowly. The other parts we're going to talk about: humic matter content, CEC, base saturation, calcium, potassium, all of that next time. Right here we're going to focus on pH and why pH is so important to growing good turf grass or good crops for that matter. This is the most important diagram for you to remember that explains pH. When our pH is 6.5, or a little bit above, between 7 and 6.5, you can see, if we draw a line up, that nitrogen is going to be very available. Phosphorus will be at the tail end but still available. Potassium and sulfur available. Calcium and magnesium available. Boron available. Copper and zinc at the top end of the other side. Manganese is still available, not bad. This color here would be not available. This is lowly available, and this is very available. Aluminum is not going to be available at that pH, but that's good. Aluminum toxicity is probably more of a problem when we have it low pHs, but molybdenum will be available. So you see, in order to have nutrient availability from the soil, we need to have a neutral enough pH that the plant can remove those nutrients from the soil where they're sequestered on the cation exchange capacity. So very important diagram. A lot of times these will be drawn like this as an oval, so more available in the middle, less at the end, and actually it would come off into here because this is available, and only over here in this lighter pink color is where nitrogen would not be available. So at pH is below 5 and pH is above 8, we would start to get problems where nitrogen's not going to be as available as we would like it to be to have good, healthy plants. So, liming. We often talk about liming. When pH is too low, too acid, we're going to add lime. I'm going to discuss in the next few slides how lime works. But one thing to remember is don't lime without a soil test. Always get your soil test. It will tell you what you need to do. And an example of that is in New Jersey for a while, there was a recommendation to put 2 pounds of lime down per 1,000 square feet every year. Well, we started seeing pHs of 8 and 9, and there's a disease called summer patch. Well, it turns out summer patch thrives in high pH environments. We saw a lot of summer patch because of this recommendation. People were just putting down more and more lime. So you want to lime when it's cool, and only when the soil test tells you should lime when you have low pHs. And it depends on the crop. Centipede grass likes a 6.2, 6.3 pH, not above 7. So we're going to lime less in the sandhills with centipede because it evolved in these sour, more acidic soils. It's difficult to get lime down below the surface, so it's important to get your soil test done before you do establishment, before you do renovation, so that you can get that lime and till it in, or even put it on when it goes into the coring holes. Mix it with your top dressing mix right after you aerify to try to incorporate and try to get the pH changes to work their way through the soil instead of just being on the surface. buffer. So we've got soil is a buffer, aspirin's a buffer. And what a buffer does is it resists the change of pH. So oftentimes, and I even like to think of a car tire is one way. The difference between a car tire and a bike tire. A car tire, if you press the valve for a second, a little bit of air is going to come out, but it's not going to drastically change the pressure in the tire. Where on a bike tire, a high-pressure race tire like we use for racing bikes, if you press the air valve, it's going to, in 1 second, you'll lose 10, 20 pounds of pressure. So a buffer is giving some buffer to that change. So on a well-buffered soil, so with lots of cation exchange capacity, when we add acid like sulfuric acid, it's not going to change the pH very much. On a less buffered soil like sands, if we added sulfuric acid to that, we would get a very rapid increase in the amount in the pH and the reading of the pH. Here's a picture of that we showed already, but this clay soil has lots of nutrients in there. Those are all connected to the soil micelle, to the cation exchange sites, where in the sand there's a lot less in there. So if we were to add a bunch of H+ through sulfuric acid or any sort of other acid, in this one it's not going to move that much. It's not going to change. It might displace one of these calciums, will be released and leached. But here, it's going to release a bigger percentage of the total cations, changing the pH and also making it more difficult. So a less buffered soil like sand is more difficult, and we've been talking about that quite a bit, and that's a theme in this course. It's better for drainage. Water moves through it faster. However, nutrients move through it faster also. So here's our micelle. So we've got our graph. So we've added our lime, our calcium hydroxide, 4CaOH2. And what happens is this splits. So this is done in the soil solution, so in water. We get 4Ca2 pluses, which are cations. Those are going to come down here and displace those hydrogens and those aluminums. And then we've got 8 OHs, hydroxyls. So the equation is balanced. The hydroxyls are going to come down here and bind with the hydrogens that came off of this micelle right here and form something I like to call hydrogen hydroxide, HOH, otherwise known as water, H2O. Okay, harmless, negatively balanced stuff. Then we've got our aluminum, which is going to come down here, bind with water to form aluminum hydroxide, which is negative, so that will leach out through the soil to get rid of that aluminum that we don't want. We don't want aluminum toxicity and leave us some hydrogen. So a little bit of acid will be left behind, but the pH will decrease because we've taken up this acid. So more acids. So interesting little stuff going on. These are cation exchange capacity sites on the clay. The micelle, that's a good vocabulary word for you to know. That will be on the final for sure. And this is a slide that you probably want to study and be able to go through and tell where the different components are coming from in the chemistry of this. So how much lime to apply? There's 4 factors in that. The present pH. If the pH is 3, we're going to need to add much more lime than if the pH is 6. What pH are we trying to get to? If we're growing Kentucky bluegrass, we're going to need more lime than if we're planning on growing centipede grass. What is the cation exchange capacity? What's the buffering capacity? How much are we going to have to move that? And the soil test will tell us that. We'll talk about that next time. And what material are we going to use? Are we going to use dolomite? Are we going to use just plain lime? Are we going to use pelletized lime or powdered lime? Powdered lime is probably going to change it faster, but it's more difficult to put out. So lots of decisions to make. It's a pretty simple math calculation to figure out how much lime you're going to need once you know the present pH, the desired pH, the buffering capacity of the soil, and the liming material. And it's also better to add less and track it over time and see how much you're changing it, because these changes do come slowly. And it's very best to do those once you've been able to till the soil. So CEC, here's just a general chart of what CECs different soils have. The higher the CEC, the higher the buffering capacity. Sand 1 to 6, we see very low. Clay 80 to 120, the highest soil. But as you see, organic matter, peat moss, between 150 and 500. So if we add a little bit of this to that sand, we get sand green. So we double or triple the cation exchange capacity, and that's why we add that, because to still keep those drainage qualities, but to also have the cation exchange capacity. The only problem with organic matter is it's variable, it decomposes. So in some high temperatures where you're not adding a lot, the organic matter will go down, but in most situations on a putting green, organic matter is going to go up because we're adding enough nitrogen that the plants are putting down dead, dying, decaying plant material, which becomes organic matter, which has cation exchange capacity. So even in a pure sand, we're eventually going to raise that CEC through the organic matter that's in there. Sodium. Sodium is our enemy. We do not want salt in our turfgrass systems. It will harm the soil structure. If we have nice colloids or things like that, it will break that apart. It will cause the plants to basically suffer from lack of water even when there's water there, because the salt will pull moisture out of the plants. Calcium sulfide, gypsum, can be used to displace the salts. People often talk about a sulfur burner. If you have water that has salts in it, you can use the sulfur burner to displace some of that cations. Calcium takes the place of the sodium on the soil and forms sodium sulfide, which leaches out. So one of the problems with salt, one of the answers to salt is more water. So this is a situation when you have salty soils, you need to add more water. So this is one of the problems they have out west. They've got these soils that have accumulated salt over time, and the only way to get rid of that is to use even more water in a situation where water is one of the limiting factors. So if you get out west or even at the beach here, you can get into some soils that are salt laden and can be a problem. And the greenhouse can be really bad for that because the water never gets leached through the pot. So we're going through evapotranspiration, pulling all the salts to the top, and they can get so accumulated so much at the top that they kill the plants, actually. So salt is something you need to check for in the greenhouse quite a bit. And Ms. Westman hopefully can add a little bit to you about that. So most important graph, know where, at what pH, what elements are available, and a lot of your problems can be maintained by between this 6.5 to 7 range of good pH. So that's it for this second smaller part. A lot of important stuff. If you might want to watch that again, or at least go over the slides and make sure you understand what lime does and how pH is so important to plants.